Hello and welcome to our vulnerability research and fuzzing training. Here we will go through the multiple methods to find 0 days on Windows-based software. Um, our examples are going to focus a lot on Windows and x86. However, a lot of the techniques and even tools that we use can target non-Windows platforms like Mac and Linux, and also non-x86 architectures like ARM. We'll go through some simple examples and some really advanced state-of-the-art techniques for fuzzing targets, including userland targets, kernel targets, and potentially hypervisors. And we'll look at some advanced harnessing techniques, like file system-based emulation to turn file system-based fuzzers to in-memory fuzzers, um, kernel hooking to dump corpus from arbitrary kernel targets, and more. A bit about me. I manage the trainings at Signal Labs. I also am a security researcher at Microsoft, focusing on Hyper-V, hypervisor vulnerability research. And as a part of that, I've done a lot of fuzzer development, including a box-based fuzzer, which has resulted in a lot of updates and contributions to the box emulator. For this set of slides, which is typically comprises a day one of effort, we're going to cover some Windows and x86 fundamentals that we kind of need to understand before we get into fuzzing or finding 0 days in a target, since they'll typically build off things like debugging and reverse engineering a target. We'll look into an introduction to fuzzing. We'll play around with a simple example to get started and get familiar with some of the tooling and techniques before we move on to more advanced modern techniques. We'll take a glance at crash triaging techniques using things like time travel debugging and how that can assist us in both crash triaging and reverse engineering in general. And then we'll also focus a bit on performant fuzzing, which is going to be a common theme throughout the rest of these slides, where we're not just interested in harnessing a target to get it fuzzing, but we're also interested in getting the most performance we can out of our fuzzer. After all, if the more performance we get from our fuzzer, the more time we save in the long run. When it comes to finding 0 days in our targets, there's a couple of approaches. We can pretty much split them into two buckets. The manual effort bucket, which is mostly static or dynamic analysis, things like reverse engineering the target, debugging the target with a live debugger and stepping through it, or reading source code. And then there's the more less hands-on approach, which is fuzzing, where you might have a lot of effort initially to write your fuzzing harness and kick off your fuzzer, but once that's running, you can let it run in the background. With this static and dynamic approach, it's typically good for smaller code bases because you can take the time to understand the target completely, which does make it more time consuming. And it's usually a one-shot thing in the case where if I reverse engineer a target today, that'll give me an understanding of how it works and any vulnerabilities and such at this point in time. But 2 months down the line, that reverse engineering I did 2 months ago may not hold. There may be more bugs, there may be less bugs, but I won't know until I redo my analysis all over again. With fuzzing, that can be overcome with continuous fuzzing, where you write your fuzzer once, but then your fuzzer continues running in the background such that even if the product gets updates, those updates, for the most part, are unlikely to break your fuzzer, depending on how it's architected, such that your fuzzer can continue fuzzing the target even after updating the target. So doing an approach like that can result in continuous fuzzing, where even if the target updates, you're still hitting that updated target. You don't need to spend time or too much time reverse engineering the target all over again to find bugs, which makes this good for complex code bases. You don't typically need a complete understanding of the target. You just need a good enough understanding of the target to write your fuzzing harness and kick off the fuzzing session. And I guess one thing I should clarify is what is fuzzing, right? To begin with, we have some target. The target passes controllable input. If it's a PDF viewer, PDF viewers read PDF files, and PDF files we can control the content of. I can open it in a hex editor and modify bits. I can use APIs to write to the file on disk or whatever I like. Um, Alternatively, it could be an application that takes a command line argument. Again, I control that command line argument. I can put it as whatever I want. It could be something that passes a network packet. In that case, the target could be listening on a port, and I could just arbitrarily connect to that port and send whatever packets I want to that target. So when it comes to fuzzing, we typically have a target that passes some sort of input that we either have direct or indirect control of. And then we find the parsing functionality in that target. If it's a PDF parser, there'll be some code somewhere in the target that actually reads the PDF file from disk and passes it as a PDF structure. In that case, we kind of loop that parsing function where we create or mutate an existing PDF file, in this case, and we feed that PDF file into the target. In the case of a network packet parsing thing like SSH, you'd find like the SSH server, you'd find the code that passes the SSH incoming connection packet and things like that, and would form our first input or mutate an existing one, which is going to be our packet in that case. We feed that input to the program such that the program passes our packet or passes our PDF and does things like that. And then when it's finished parsing, we go back to the start of the parsing function in the target or call the function again with our next input. And we keep calling the parsing function with new inputs until the target crashes. Maybe in the case of a PDF viewer, there's a header in the PDF structure that, based on its value, the target may arbitrarily dereference a user-provided value in the PDF, which means we can cause crashes by providing invalid pointer values there that it'll dereference. The main point is we keep looping the parsing functionality in the target with new inputs until we find an input that crashes the target. That's a very kind of basic overview of what fuzzing is, but you get the idea. I guess I can take a moment here to quickly visualize that as well. So say we have here PDF parser.exe, right? Actually, you know what? Let's just do Adobe PDF Viewer. Make it more clear. Now, in Adobe, there'll be some sort of code. Let's call this code, let's use a rectangle. Let's say that this is PDF parse.dll. And say that this DLL actually contains the parsing functionality. Parse PDF par. Say Adobe PDF Viewer has the DLL in it called PDF parse DLL. And that DLL has a function called parse PDF that takes in a string, a car pointer string called path, which is going to be the PDF path on disk. Now this is just an example. This may not be how it's actually architected, but this may be how it is. You won't know until we look into it. Now say parse PDF. Okay, so that's a DLL, that's an exe. Let's use something else for a function. So this is the parse PDF car pointer path function, and the parse PDF function, sure, I'll make it this way. So this DLL has this function in it. What does this function do? This function will do a few things. Let's say it's 1. Load path as file from disk to parse the file bytes as a PDF. So return parse PDF struct. Okay. So say Adobe PDF Viewer calls into PDF parse and calls parse PDF to parse a PDF file. And then once that PDF file is successfully parsed, Adobe PDF Viewer gets back some sort of structure representing the parsed PDF, and then Adobe can present that structure on the screen in its GUI or something like that, right? This is an example. In parsed PDF, it'll load the path that we provide as a file from disk, which could be something like C drive temp my PDF.pdf. I could call that using the read file APIs. So maybe one ends up as, first create file, and then path, and then like read file. This would be like handle equals to create file, and then read file handle buff, where buffer is a allocated buffer to hold the bytes from the file. So as it loads a file from disk, it'll just create a handle to it, read it into a buffer, and then at point number 2, it has the buffer. And then maybe there's another function that takes in this buffer and reads it in as a PDF. So maybe it knows that buffer at offset 0 contains a header, buffer of offset 100 contains metadata like file creation type and stuff, and then from buffer 1000 to the end of the buffer contains maybe more data, like the actual data of the PDF, the text, embedded images, and all that sort of stuff, right? Maybe it passes the header to see what version of a PDF it is. Maybe it passes the metadata so it knows things about the file, like its creation date and things like that. And then maybe it passes the rest of the data to actually get the text and images from the PDF or whatnot. And then 3, it can kind of get the header, get the metadata, get the raw data off it, maybe format it in some sort of structure and return that structure to Adobe PDF Viewer.exe that can then display it on the GUI and stuff like that. It's a rough example of how the target might be architected. Now, Alfuzzer might wrap this parsed PDF function. Actually, instead of that, what I can do is say we have fuzzer. Actually, what I'm going to do is call this harness. Our harness is what is interacting with the target. So our harness might directly call this parsed PDF function. So our harness might directly call this this parsed PDF function, providing it the file path to our input on disk we want to target. Parsed PDF will pass that PDF target. And potentially during the parsing process, maybe it does something dangerous and interprets a few bytes from the PDF file as like a size or an index into a buffer. And perhaps since we control that value, we can actually index out of bounds of the buffer and get like out of bounds reads and writes and all sorts of fun, right? That's what we're looking for, those types of bugs and crashes. So say our harness runs parsed PDF on the target and it finishes parsing, comes back to us, there was no crash. So we then generate new input or mutate. We might mutate an input. And then once we have new inputs, we call that parsed PDF function again. And we pretty much loop that. We call parsed PDF with one input, hit the parsing functionality. Once that's done, we generate or mutate another input and call the parsing functionality again. We generate, mutate another input, pass again, new input, pass again, new input, pass again. You just do that as a loop until you generate an input that crashes the PDF parser. Now, why call pass PDF directly? Well, when you think about Adobe, right? Adobe has a bunch of functionality in it, including a full graphical user interface and all that stuff. And when we're fuzzing, we don't want to have to double click Adobe, wait for it to open, hit File open, and then double click our PDF, and then close it, and then open it again, and then hit File open and open up a PDF again. Like that's super slow. So instead, we find the actual code in the target responsible for passing the PDF. And if it lives in a DLL like this, our harness can actually load PDF pass directly into our process space, such that when we're calling pass PDF, it's not the pass PDF that lives in the Adobe Viewer process directly. Instead, we can find where pass PDF lives on disk, right? Say it lives in C drive, program files, Adobe bin, and it's right there as an example, right? If it lives there, we can use like the load library APIs to load pass PDF into our own process, such that when we're calling this pass PDF functionality and such, it's actually not not the one in the Adobe, well, it's not running directly in the Adobe process. Instead, it's running in our own process space. I'm just going to say fuzz to represent the fact that we're sending input or send input to pass PDF. So when we're actually fuzzing, this is what it's going to look like. Our harness, which is our own code, is going to load the code responsible for the passing directly into our process space. Now with snapshot fuzzing, it looks a little bit different, but for now, this is one method and a very common method for fuzzing. And this, in this case, is a DLL, but it could be an exe. You can pass exes to load library and load it into your own process space. It can be whatever, but in this case, it's a DLL. Once that's loaded into our process space, we can find where the pass PDF function lives in that target and call it directly, sending it the input. And this is how we would fuzz pass PDF. Because if we find a bug here, well, we should be able to hit that bug in the actual Adobe process, because we would know that we can hit this function simply by opening a PDF with Adobe. We're just harnessing it in such a way that we can call the responsible passing function very, very fast with new inputs instead of having to interact with the GUI and do things like that. We're skipping over that part for speed in our fuzzer. So this is how general fuzz cases work. I'll walk through full system snapshot fuzzing and how that differs to this approach a bit later. But this is a very common approach where you have your harness. It's called a harness because it's harnessing the target to send it input. Now, our harness is responsible mostly for sending input to the target, right? Maybe it has to load the DLL into its process space. Maybe calling pass PDF takes a car path, and maybe it takes something else. Maybe it's a this call, and the first parameter is actually a pass PDF object. And maybe a pass PDF object needs to be initiated or initialized by calling its constructor, which could be pass PDF object new. And that just takes a buffer. So perhaps before we call pass PDF, we need the first parameter, which is a pass PDF object. Maybe that object is created by calling the pass PDF object new constructor, passing it a buffer of a large enough size to hold the allocated object. Which means before we call pass PDF, we need to call this pass PDF object constructor with a buffer to get as a return value the pass PDF object that we can then pass to this pass PDF function. because the function now requires the object and the path, no longer just the path. In this case, our harness would load past PDF. Our harness would call the constructor to get the past PDF object, and then our harness would have all the parameters necessary to call past PDF, and then we could fuzz past PDF. Depending on how many parameters and what the parameters are for your parsing functionality, you're going to have to do some reverse engineering to figure out what the parameters are and how you can construct them to call the parsing functionality directly. And we'll do this with a real Windows example later on so you can get a feel for how that works. Now, what about our actual fuzzer? So we have our harness, but there's going to be some process running somewhere that is the actual fuzzer. Now, what the fuzzer is responsible for is a few things. One is inputs, input management. This includes things like generating inputs, mutating inputs, saving interesting inputs, and the like. So, for example, maybe we have an example PDF file that we found from the internet, and that's going to be our first input to this PDF parser. Once we ran this parsing code against our first PDF input, we want to generate or mutate a next input. So what we can do is maybe we grab the first PDF and maybe we flip some bytes or flip some bits in it. That'd be the mutation phase, where we are modifying an existing input to create a new input. Or perhaps we know how to create a PDF file because we read the specifications of what is a PDF file, and we just generate a complete new input from scratch. There are two methods. And then we feed that new input to our harness, maybe using shared memory or something else to communicate with the harness. And then our harness will feed that input into the target. So the fuzzer is more generic. It does generic things, while the harness is target specific. Loading up the DLL responsible for parsing a PDF is for Adobe is super target specific. While the fuzzer, just flipping bits in things and sending it to our harness, that's very generic. The fuzzer will also get coverage because for the most part, we're looking at coverage guided fuzzers. So this would be like collect coverage. Now, what is coverage? Say in parse PDF, there's an if statement. If PDF header equals to 0xFF, do stuff, right? And then maybe else if PDF header equals to 0x1231, do other stuff, else do more stuff, right? In this case, if the PDF header matches a certain value, it'll do something. If the PDF header matches another value, it'll do something. If the PDF header didn't match any of those values, it does something else. These are three branches. Now in assembly, when it's actually compiled, it might look like something like comp rax 0xFF or something like that, and then it'll be like jump not 0 to some location and maybe label 1, some location in memory. And then if that didn't work, it'd be comp rax 1231, jump not 0, label 2. And then if none of those matched, it'll just be an arbitrary jump to like label 3. This is just a very basic example where it compares rax, which might be the header from your PDF, to the value. And then like, it might jump depending on if it matches, if it doesn't match, and types and things like that. So say we hit this comparison instruction, and say this comparison instruction is at address 0x111, maybe this is 0x112, 0x113, 0x114, 0x115. Okay, this is all made up stuff, but it's enough to kind of demonstrate what I mean. So this address on the left is the actual virtual address of this instruction in memory. So we know with assembly, right, we have a program counter. In x86 64, that is the RIP register. So say the first instruction, RIP is at 0x111. That's the comparison instruction. RIP is then going to hit 0x112 as it goes to the jump Z label 1. Now say jump Z label 1 is at 0x200. Label 2 is at 0x300. Label 3 is at 0x400. If we pass the condition, we're going to jump to label 1, which means RIP will be 0x200. Alternatively, if we don't pass this condition, it's going to go down to the next instruction, which is 0x113. Which means our instruction pointer will definitely hit 111 and 112. But then as soon as it gets to this, as soon as it passes 112, it has two possibilities. It can go to 113 to the next comparison, or it could have satisfied the conditional and jumped to label 1 at 0x200. So we have two possibilities for RIP here. Now coverage, with coverage guided fuzzing, we save inputs that hit new coverage. So if input 1 went down the path of not satisfying the conditional, so I went through 111, 112, and then 113, that fuzz session might save that as an input on disk because it hit new coverage. If the next time we fuzz, our new input hit the exact same code path, 111, 112, 113, that input may not be saved because we already have an input that hits that path. But if we then generate an input that hits a different path, perhaps 111, 112, and then 200, because it took the jump, that input would have hit new code, right? It satisfies the jump, whereas the initial input that we used didn't satisfy the jump. So now we may save that new input to disk as well, which means we'd have two inputs. We'd have two inputs saved. We'd have input 1 that went to all the way to 113, right? It didn't take the jump. And we'll have input 2 that did make it to 0x200 because it took the jump. And we do this because we're interested in inputs that hit new code. And also, since our fuzzer can track this sort of thing, normally you can visualize this in something like IDA Pro or Ghidra. You can visualize the code path taken by your fuzzer for any input. If I view the coverage taken by input 1, perhaps it didn't satisfy this check and it went all the way to 115. So you would see that in the instructions that it took. Likewise, if I visualize input 2 and it did take the jump, I would see that it took the jump. I would see the instructions executed are the instructions of where it takes the jump path. And normally you want to encode this as, you want to take the raw instruction, like say RIP 0x111 is actually the DLL, which in this case is PDF, what did I name it? Pass PDF. So pass PDF.dll plus an offset, say 0x111. Right, because pass PDF.dll, because of ASLR and stuff like that, is always going to be loaded at a different address, but the offset is going to be the same. The offset of a function in the target is always going to be the same for that specific version of the target. So we can convert the raw virtual addresses of the instruction pointer into a module name, which is pass PDF.dll, and an offset. In this case, I'm just going with 0x111. We'll see how offsets work from module names later when we work with them more. But that's generally how you want to visualize it. And that is how code coverage works. Now you might say, how do I actually inspect the instruction pointer of the target? How do I get this code coverage? Well, there's a couple ways with hypervisor and emulator-based approaches. So first of all, emulators, right? Emulators emulate the target. Emulate the target, right? By emulating the target, it means that they keep track of CPU state. And by keeping track of CPU state, they keep track of RIP, RAX, RCX, RDX, for a 64-bit Windows target. An emulator will be emulating everything such that it has a CPU state and it has the status of all registers as its emulating target. So it can just directly query the instruction pointer register. That's very easy for emulators. For hypervisors, they can always use the hypervisor. Well, whenever code. Okay, so hypervisors, they run as a higher privilege level. So I'm going to say L0 is the hypervisor, and then L1 equals to the guest. Now, when code is executing in L1, it's executing in the guest. But at some point, the guest may transition back to the hypervisor, such that you're running back in L0 hypervisor. And the hypervisor can always query the L1 CPU state, which means it can get the L1 CPU state structure of like RIP, REX, RCX, etc. So since there's always a way for the hypervisor to query the CPU state of the target, assuming we're talking about just regular virtual machines and not like confidential computing type thing, the hypervisor can always get the CPU state of the guest, which means it can directly query the instruction pointer of the guest and get it that way. Now, what about things like the tools we'll be using? The tools we'll be using are, to begin with, are userland tools like WinAFL, AFL++, Jackalope, HongFuzz, etc., etc. How do these do it? Well, these instrument the target in some way. With WinAFL, and what we'll be using is there's a tool set called Dynamo Rio. There's also like Intel PinTool and TinyInts and more, but we're going to be using Dynamo Rio. Dynamo Rio is an instrumentation set of tools where it can load up a userland binary and modify it such that it introduces like shadow stacks and can get callbacks when certain things happen and things like that. And it's Dynamo Rio is what's going to provide our fuzzer with the coverage information. You can look into the internals of how Dynamo Rio instruments the target such that it can get callbacks from it and query the instruction pointer and things like that. We're not going to dive too deep into the internals of it. We're just going to learn how to work with it to get that coverage information and how it works with WinAFL when we do our general fuzzing. But you can feel free to look at something like that or TinyInts and that and see how coverage works. There's also something like Mesos, which is pretty much just sets breakpoints everywhere, such that when the target hits a new branch of code, you get a callback from that in the form of a breakpoint in the target. Because you can act as a debugger for that target and get notified when breakpoints occur. And then that's your kind of coverage feedback there. Again, when it comes to fuzzing, some code bases are complex. You know, when I think of TCP and UDP connections, there's a kind of large state machine there, right? At any point in time, the connection could be connecting, negotiating, handling specific packets like SYN, FIN, ACK. It could be closing, and perhaps sending different data while it's in different states can cause different things to happen. So it can be much easier to stress that state machine and the inputs it handles while in various states via fuzzing instead of manual analysis. To reiterate, a fuzzer is generic, usually to a point, and may be specific to a platform like Windows or an architecture like x86, but it's usually not target specific, like for PDF parsers only, or for network parsers only. It'll handle input generation, mutation, and saving interesting inputs, as well as instrumenting the target to run the target to get coverage feedback, and also to reset the target or looping the target parsing functionality. And obviously, it should also handle catching and reporting crashes, or timeouts in the case where you're looking for infinite loops. A harness is the target specific code, like targeting a very specific version of Adobe, for example. It handles feeding the input into the target, And we looked at how an example of that could work. Fuzzing back in the day used to just be feeding random input to a target and seeing what happens. It's kind of funny that this can still work, but for the most part, we want to fuzz more intelligently using code coverage and other metrics. There's also grammar-based fuzzing, where you can define a set of rules and you can have inputs be generated based on those rules. This is similar to how syscaller generates inputs, if you're at all familiar with that. In this case, we can define an identifier tag that we can say equals to a const, and another identifier tag that is a static, which means that identifier tag can be a const or a static. We have a var name, which I'm just going to say is my value. We have an int32, which is a range starting from 0 to the maximum int32 value of f's. And then we can define an int32 variable is an identifier tag space a var name tag space equals space an int32 tag. Now with this kind of tag logic, a generator might be able to generate an int32 variable by saying, okay, I need to grab an identifier, which means it's a const or static. In this case, it grabs a const. Then it needs to grab a var name, which I define as my value. So it defines my value there. Then it needs to grab an int32, which can be any value within this range. And in this case, it could generate 1337. So by using this tag logic that builds upon itself, or a grammar-based like input generator might generate this line, const my value equals to 1337. And since it's very good at generating text based on a list of rules, this is the type of thing you see in like JavaScript DOM-based fuzzing. If you look at a tool called Domato, which is like tomato but with a D, you'll see that they use grammar-based fuzzing like this. And you can also use this for binary values. I recommend looking at syscaller and the syscaller definition files to see how syscaller for Linux does input generation based on a similar looking grammar as well. It's just one way of doing input generation. We're not going to dive into it too much, but it's something to be aware of because it might be useful for your targets. You could also go the way of automation, where you can automatically generate grammars and then have a fuzzer automatically generate inputs based on that grammar. Again, take a look at Domato, take a look at syscaller if you're interested in reviewing those techniques. You'll notice when it comes to fuzzing, there is a lot of techniques, a lot of different methods, especially when you're diving into the specifics of like input generation. There's whole papers, research papers written on different ways to do input generation and input mutations and interesting ways to tweak your fuzzer, to do smarter ways of catching comparison instructions and decoding those comparison immediates and putting that into your input and all sorts of things. But they're things that once you wrap your head around the entire process of fuzzing and get familiar with it, you can look at those papers and look at those techniques and implement it yourself or use a tool that already does it and understand it. Most fuzzers, like what we'll be using, come with some generic mutation strategies, like just flipping bits, taking byte slices of various sizes and flipping those. Input splicing, which is just merging multiple inputs together. They might have a dictionary of keywords or key values, like the maximum int value or the lowest int value, or the maximum 64-bit value, signed and unsigned, and things like that, so that they can do generic mutation on your target. Now, if you know your target needs a very well-defined input, then you may forego a lot of this generic stuff and just write your own mutator that mutates the target in such a way that it still conforms to the specification or what's required by your target. If your target expects a checksum of the entire buffer as like in a certain offset in its input, you'll need to handle generating that valid checksum either at input generation time in your custom mutator or in your harness, where your harness receives the input and then before your harness sends that input to the target, perhaps your harness modifies it to include that checksum. You can do it either way. Coverage feedback, as mentioned, it's by taking at first step the raw instruction pointer address and then turning it into a module base plus offset and then like saving that on disk somewhere or just being able to view that. The fuzzer will use coverage to determine whether it saves an input or not. And we can also use coverage to visualize what code paths are hit in our target. And we can use that visualization to identify gaps. This sort of feedback is super important for detecting how your fuzzer is working. Which parts of the code are you hitting? Which parts are you not hitting? If you're fuzzing an image parser and you're noticing that none of your code is hitting the JPEG specific code, you're hitting maybe PNG code or GIF code passing, but you're not hitting the JPEG passing code or whatever. You could visualize that with code coverage, and then you'll know your gaps, and you can work on generating an input that will hit that gap, like perhaps providing your fuzzer a JPEG file so that it can use it as an input and hit the JPEG passing logic in the target. Your corpus, when we talk about corpus, that's your initial set of inputs. It practically determines what code you hit, because if you're fuzzing an image parser but your corpus consists of only JPEGs, it may be unlikely that your fuzzer will generate a valid PNG and hit the PNG passing code. It depends what goes into hitting a PNG and how complex it would be for your fuzzer to just generate a valid PNG type such that the target will go down its PNG passing code instead of its JPEG passing code. But if my corpus, my initial set of inputs, consists of both a JPEG and a PNG, then my fuzzer will definitely hit both paths in the target to begin with. And to generate corpus, if it's a common type, you can just pull samples from the internet. If it's some obscure type, but there's an RFC for it, you could generate an input yourself based on the RFC. And if the target's closed source, but there's an open source version, you might be able to just pull the open source version, view the source code, and use some of that information to create or verify your inputs first. And then there's also like decisions to be made as to how large or how small you want your input to be. The larger it is, the less effective mutating it is going to be, or the harder mutating it is going to be, because there's just that many more bytes in it. But if it's smaller, then it might not have or be hitting all the same functionality in your target, depending on what those bits that are missing are. And the point of a fuzzer is to find a crash, right? But we need to actually understand what is a crash, like what actually happens in your CPU or CPU world when a crash happens. Let's look at an example of x86 and how that works with virtual memory. Say I wanted to execute a virtual address of 1337.1337. Say it's a stack address, and in a modern program, what happens? Now, in a modern program, there's no execute stack flags, right? Such that stack addresses, if they're going to be executed, will result in a crash. But what actually happens in that process? How does that work? Well, in this case, we have the virtual address, which is 1337.1337. That's going to be executed. Now, those bits of that virtual address can point to indexes in page tables, which will then point to a final page table entry. Now, this is just how virtual memory and page tables work on x86. We'll have the top level page table, which lives in the CR3 register, which is just a CPU register of x86. And this contains the physical address to the top level page table. And so your virtual address will be deconstructed in such a way that the bits of it will point through the page tables eventually to a page table entry. Unless, of course, it's a virtual address that isn't mapped to any page. This is the case where you go to execute a virtual address that just doesn't exist in your process. In which case, while the CPU tries to find the page table entry for that virtual address, it won't, because it won't be mapped. And in that case, that will raise a page fault interrupt, which will transfer execution to the kernel, and the kernel will handle that page fault interrupt by likely killing your process. But in the case of where it is mapped, but it's just mapped as non-executable, it'll find that page table entry, And that page table entry will contain the mapping of the virtual address to its corresponding physical address where it actually lives in RAM. But that page table entry will also contain metadata. It will contain if the address is readable, writable, executable, etc. So if that page table address is validly mapped, we'll find the page table entry. But if that address is marked as non-executable because it's a stack address and your program on boot told the loader to load that address space as non-executable, then that no execute flag in the page table entry will be set, which means that the CPU will see that you're trying to execute an address that the page table entry metadata says is non-executable. In which case, the CPU will raise an interrupt. It will be a page fault interrupt. That will go to the kernel, and the kernel will have a specific page fault handler for those interrupts, and it will decode exactly what page fault error it was, and it will handle it. In the case of where we're trying to execute no execute memory, the kernel will likely just kill our process. So based on the CR3, that determines which page tables are used to decode your virtual address. And this is also how virtual address separation works between processes, right? If I look at process 1, say this is proc1.exe, and then over here we have proc2.exe. Proc1.exe will have its own CR3 value of say 0x1000. Say proc2 has its own CR3 value of 0x2000. Now, since they have different CR3s, they're going to be and CR3s are physical addresses. They're pointing to different page tables. Now, of course, the kernel could have set them up with the exact same page table. That's not normal. That would be something that you would have written custom code to do or something. Because in general, processors have different address spaces, right? If proc1 goes to, read read virtual address of 0x1337, maybe that contains the bit 0xFF. Right? Say process 1 goes to read the virtual address 1337. Now for proc1, that might contain the byte 0xFF. Now in proc2, if it goes to do the same thing and read the same virtual address, it might contain different bytes. Maybe this one's 0x12. That's because the virtual addresses in different processes don't share memory by default, right? Proc1 has its own memory space. If it writes to a certain virtual address or reads from it, it's not going to affect the contents of that virtual address in another process. We have separation of virtual address spaces that way. And that works because virtual addresses are translated based on the page tables that live in the CR3 register. And since they have different values for the CR3 register, they're going to be translated using a different set of page tables, which means the page table entry for this CR3 here, for this virtual address of 1237, might point to a different place in RAM where those bytes live compared to process 2. Now, if they had the exact same CR3, they'd be decoding memory using the exact same page tables, which means in this case, the virtual addresses will contain the exact same data. But in general, separate processes will have their own CR3 register value. And the kernel shares its own CR3. If you have the kernel, which can be like driver 1, driver 2, driver 3, whatnot, the kernel space as a whole shares a CR3 in general. There's nothing stopping your driver from creating its own CR3 page table entries. But in general, the entire kernel has its own CR3 that it shares, such that kernel memory is shared between all kernel components. That's just how it's generally architected. Now, with shared memory, what happens, right? If I had a shared memory blob, let's say this is shared mem. It'll be mapped into both targets CR3. pointing to the same physical address in RAM. So say its physical address is 0x999. But its virtual address in this CR3 might be virt address 0x222 for process 2, and in process 1 its virtual address 656. So in the case of shared memory, if it's mapped into both process spaces, the shared memory object, it can have whatever virtual address it wants in both of those processes. And I say in process 2 it's 222, in process 1 it's 656. However, it's mapped into their page tables in such a way that that virtual address corresponds to the exact same physical address, 999. Which means if process 2 goes to write to virtual address 222, it'll affect virtual address 656 in process 1, because both those virtual addresses are mapped to the same physical address, and the physical address is the actual location in RAM where that data lives. That's how shared memory works. It just maps in a certain amount of pages into the page table entries of multiple processes, such that when they interact with those virtual addresses, it all gets translated to a page table entry that points to the same underlying physical address. So that's shared memory. That's how address spaces are separated between processes, and that kind of decoding of a virtual address to a physical address can cause page table faults if the page table entry doesn't exist, if it's marked as non-writable but you're trying to write to it, and things like that. And that's how a lot of crashes happen. They happen in the form of page faults. That's kind of good to know to understand what the main cases of crashes are, and how it's detected in the page fault handler in the kernel. Yeah, in this case of what if we overflow a stack buffer into another writable variable? Right, say in the stack is laid out with a 64-bit value called var1, and then a 64-bit value called var2, and then a function pointer called var3. Now, U64s, right, are 8 bytes. And pointers on a 64-bit system and 64-bit x86 are also 8 bytes. Which means, say our program went to write 10 bytes to var1, right? Would write the 8 bytes here, but then 2 bytes would overwrite var2. This is the case of where we're overflowing the stack. We could overflow one variable and start affecting the bytes of another variable. But since these two variables may both be marked as writable, when the CPU goes to do the whole page table translation stuff for these two variables as we overwrite var1 into var2, it might see that they're both mapped into the process and they're both marked as writable, so I'm allowed to write to it. Which means this overflow won't actually be detected as a page fault. In fact, it won't be detected as any crash initially, because I'm writing to addresses in memory that are mapped and marked as writable, so the CPU sees no problem there. Which is why if I overflow var1 into var2, there won't be a crash. At least not right away, right? If the target goes to, if I overwrite this function pointer with 3 bytes, and then the target goes to jump to this function pointer, since I've modified the address of this, it may actually point to some invalid memory that would cause a page fault. But otherwise, that just depends entirely on how it's used. The initial writing of it may not actually cause a crash. Now, this is where you can do things like compile your target with address sanitizer, enable page heaped for Windows as well, and that may modify things such that we can better detect crashes. Like perhaps in between each variable, there's a guard page. Say here, there's a guard page, and then guard page, and guard page. Now, guard pages can be marked as no access. No access means that the page is mapped into your process space as CR3, but in its metadata, it's marked as no access. It's not writable, it's not executable, it's not readable. If you go to touch that address, it's going to cause a page fault no matter what. That's what a guard page is. And by inserting guard pages in between variables, it means if I overflow var1, it's not going to overflow into var2. Instead, it's going to overflow into the guard page. And when the CPU goes to view the page table entry for this guard page, it's going to see that it's not writable, it's not readable, and it's not executable, and I'm trying to write to it, so that will cause a page fault. So by using guard pages like this in between allocations or stack variables or heap allocations in the case of using page heap on Windows, we can increase our chances of detecting bugs like overflows, because it's not going to overflow into another writable variable. It's going to overflow into a guard page that will cause a page fault that we, as the fuzzer, can detect and then go, we found a crash. So as mentioned, we can use various techniques like that to kind of increase our chances of detecting crashes. Um, Things like enabling page heap using gflags on Windows, which we'll look at a bit later. Address sanitizer when it comes to compiling or potentially recompiling a target. Memory sanitizer for detecting uninitialized memory reads by marking it read after write, and interesting things like that. Now we can actually look into WinAFL, which is the first fuzzer we're going to look at and use. It's probably one of the most common Windows-based fuzzers, or at least one of them. It's a port of the AFL fuzzer for Linux with some of the AFL++ patches ported into it. It offers coverage feedback with decent mutators by default, and it uses the DynamoRio toolset for code coverage. It's been used to find many bugs in the past. It doesn't support kernel targets, only user targets. It was used in a Black Hat 2021 talk to find bugs in the Windows PDB parser, and it continues to be useful today. So it's a good one for us to get started with for our initial fuzzing. DynamoRio, as mentioned, is used by WinAFL for instrumentation. It actually redirects execution of a target to its own in-memory copy. And that in-memory copy of the target is modified by DynamoRio so that it can do things like trace code coverage, hook functions to get callbacks on branching instructions, and things like that. Now, with code coverage, we can actually visualize code coverage when it comes to DynamoRio. How might we visualize code coverage? Well, let's take a look. If I open up a command prompt and I go to where my DynamoRio folder lives, I can run dr run -t drcov -- and then the program I want to trace. Let's trace putty. C drive program files putty.exe. This is going to run putty. It's going to generate a coverage file from it after I run it. I'm going to run putty. Putty should start up in a moment. Ah, here it is. Here's putty. It's running. I can click through things. Now, when I exit putty, it's going to save that trace file somewhere on disk. I can see I've already done a few. Today is this entry here. This entry here is the saved information. Now, if I open that file, you can see it's tracked the loaded modules, all the DLLs that were loaded, putty.exe itself. And then after tracking all the loaded modules and their base addresses and such, it has a binary data of the coverage. So I'm going to open that. in IDA. If I go to eDrive, vulnerability research, code, DynamoRio. Whoops, sorry. First, I need to open up PuTTY directly. So let's open up PuTTY. I'm going to save the database in just bdrive temp. Okay, now here's PuTTY. Now, because I have the Lighthouse plugin installed, which you can grab straight from GitHub, if I search GitHub Lighthouse IDA, it's this one from GitHub. Now I can go File, Load File, Code Coverage File, and I'm going to go load the code coverage file that was produced by DynamoRio. It's right here. I'm going to open it. Now, let me regenerate my decompiler view so that it can be highlighted. I'm going to sort by coverage. And now green means that the coverage was hit in the target. So I can see here, for example, code hit all here, code hit this jump, but then code jumped past to here. So in this test case, or in this case of running PuTTY, my code didn't hit this block or this block. It hit this jump, it satisfied this jump condition, and it jumped here. You can see that in the decompiler as well. It didn't go down this path, it ran down this path. And using this, we can see that we didn't take this path, we took this path, which means we satisfied this jump. And we can use this to kind of visualize what code we're hitting. And we have an overview on the right of all the code we're hitting and how much coverage we hit in these functions. It's a good way to visualize what your code was doing. Now that this is loaded here as A, maybe I run it again, but this time that I run it, I do something different. Maybe I try to connect to a name pipe that doesn't exist. Now that did something different. I went to connect to a pipe that didn't exist and it crashed the process. So now I should have a new input and I can load this additional code coverage file, which is this one. Now I've got code coverage A and code coverage B. And you can see they hit different code. In fact, I can do arithmetic. I can say, show me all the code in B that doesn't exist in A by doing B minus A. By doing B minus A, I'm seeing all the code that I hit the second time I ran it, but excluding the common code between the second time and the first time. Which means if I go to main, it's not highlighted. See, in our first case, we obviously hit main. And in our second case, we also hit main. But in this comparison, B minus C, it excludes main. Because B minus C is going to show us only the code that is unique to that second time I ran PuTTY. And it's going to exclude all the common code between the second time and the first time. This can be used to like isolate functionality in a target. If I run a target and I don't log in, and then I run a target again and I do log in, and then I do the login one minus the common code between that one and the first one, then the functionality left that's highlighted should be directly related to the logging in functionality. And you do all sorts of arithmetic between the captured log files to isolate functionality and assist in your analysis. libfuzzer is another popular fuzzer that leverages the LLVM toolchain. Libfuzzer is the fuzzer that you'll use if you have source code for the most part, because it requires source code and it compiles in instrumentation instead of doing it at runtime like DynamoRio. You can also compile your target with address sanitizer and things like that to assist with catching crashes. And this approach is mostly preferred over other fuzzers when source code is available. And that's the biggest limitation with this. It requires source code. But it's good to know if you are doing source code based fuzzing of like open source tooling. Symbolic and consolic execution based fuzzers. Well, first of all, symbolic execution engines have a variety of uses in program analysis, where they're used to solve constraints. Typically, so some of those include like Microsoft Sage or Richard Johnson's eGAS, which is just Sage backwards. There's also Miasm, Triton, Manticore, stuff like that. We're not going to be using them. They're a bit slow and impractical in the most part, but they do have niche uses, especially in the case of corpus generation and things like that. What symbolic execution pretty much is say this is the code path I want to hit, right? Say, look, we have these instructions, and we have comparisons here. Some sort of comparison here, jump greater than, some sort of comparison here, jump not zero. What I can do is say, tell the symbolic execution engine that I have control over, say, RCX, and I have control over, say, this location in memory. Tell me what values I need in this location in memory and in RCX to satisfy this jump, or to satisfy this jump, or to not satisfy this jump and go down this path, or to not satisfy this jump and go down this path. Pretty much I can give it these constraints, and the engine can analyze this assembly code and determine what my input value needs to be to satisfy this jump or to go down this path of code. Like it can generate that information to tell me what's needed in my input to go down certain paths. Now that can be good for input generation because it can analyze your target and generate inputs that hit or satisfy different comparisons. But it is a very niche aspect. So it's good to kind of know about it if you want to explore that more in your own time. And now we can take a moment to look at the WinAFL 1 exercise slides and solutions. The goal here is to compile the example harness GDI Plus that's included in WinAFL. Optionally, you can capture an execution trace and view coverage, but we really want to get the base example harness for WinAFL fuzzing in WinAFL. You can go to the WinAFL 1 exercise folder now, view those slides, or the talk that walks through what we need to do, and then there's also solutions included.